So I'm Sean Middleditch. This is a lecture on C++ messaging systems. So a little information about myself. I'm a senior here at DigiPen. I've done a few games. You probably haven't ever heard of most of them. Subsonic, Sonar, Core, nothing too spectacular there. I really like game engine architecture. That's why I started the club and get up here and talk and try to get you guys to come up here and talk whenever you're interested in doing so. So this presentation is going to be about messaging systems in a C++ application. In particular, what messaging is used for and some general ideas on how to implement it. I'm not going to go over a lot of concrete, here's code you can cut and paste in your project. Part of that is because this is a school and you are expected to do your own code. But this should get you on the path to figure out how to do your own messaging systems. Slides are also completely picture-free, but I do have some code samples which should hopefully make up for lack of pictures. All right, so the basic idea of what messaging is. Messaging is a way of allowing different components in your system to communicate with each other. So you're used to the idea of component in terms of Chris Peters' lectures. Here, just mean different parts of your application. For instance, the graphics system needs to be able to talk to objects that can be drawn. The physics system needs to let logic know when objects have collided. There's a lot of different ways to get this information sent back and forth between these different modules and components in the system. There's a lot of ins and outs on how you can make this work efficiently, make it work easily, and we're going to go over some of those now. Messaging is a way for a specific sender to let one or possibly many other objects know that something has happened. So the idea here is, say for example, you have the physics engine just detected two objects collide. It's going to let those two objects know that they collided. There's also a couple other ways you can do this. You might want to have another object who wasn't even involved in the collision know that this collision happened. So we're going to go into patterns for dealing with that as well. So the four broad types of messaging. The first type is called broadcast. In the broadcast system, whenever you have a message that you want to notify other components about, you just say, hey everybody, this happened. So going back to the physics example, when two objects collide, the physics system tells everybody that these two objects just collided. It's really easy to implement, but as you can imagine, there's a lot of work going on sending all these messages to everybody, including a lot of objects who really don't care that these objects just collided. The second method is direct delivery. This is where the object says, hey, you need to know about something, and I'm going to tell you, and nobody else knows about it. An easy way to think of direct delivery is as a method call. This is essentially a form of message passing. In pure object-oriented systems, methods are actually defined as messages. So there's kind of a neat corollary there. The problem now is that it's inflexible. If you have these two objects that are colliding, but some other object needs to know, like you want to have a game score system keep track of every time the player runs into something, that object can't watch these things. They have to notify the systems themselves, and it's a lot less easy to deal with. The third way is observers. This is the most common way you're going to see in more complex game engines. We're going to go into that in quite a bit of detail in a bit here. And there's publisher, subscriber, which is kind of, you can kind of think of it as an advanced version of observers. I'll go into that very, very briefly. So there's bubbling. Bubbling is another concept in messaging that comes up a lot. It is not something you usually use in games. The idea of what bubbling is you have this parent-child relationship between objects. For instance, you have a scene, and in that scene you have actors. And then maybe one of these actors is carrying a sword. The idea of bubbling is saying something happened to the sword, so we now want to automatically let whoever owns the sword, which is the actor that's carrying it, know. And then after the actor processes that, you can tell his parent, which would be the scene itself, that something happened. And you can even go the other direction. If something happens in the scene, you can let all the scene's children know, and so on and so forth, which is actually just a form of broadcast. This comes up a lot because if you start using messages for your UI systems, you basically need bubbling. So if you look up HTML bubbling, DOM bubbling, you're going to get a lot of information about that. It's pretty UI specific in most use cases though, so I'm not going to go into that in much more detail here. So there's some terminology confusion I see a lot. People get a little confused about the difference between messaging and events and signals. The short version is that they all mean the same thing. I'm going to use the word messaging. If you prefer events or whatever, that more power to you. Doesn't really matter a whole lot. So uses for messaging. We went over physics, letting other objects know when things collide is a good one. Like I said before, the method calls in pure object-oriented systems are a form of messages. So you can think of this for a method call on your physics component. There's a method onCollided. You can call that from your physics engine, and this is essentially your physics engine sending a message to the physics component saying, hey, you just collided with something. And of course, this is a direct dispatch because with a method call, you can only call that specific method on that specific object. There's not a lot more you can do with that. We do, however, make a particularly big distinction in games between method calls and messages. One of the reasons is that messages can contain additional metadata. So if we have a message from the physics system to the physics components, it's not just going to say you collided with something. We have extra information. What did you collide with? When did you collide with it? What kind of collision? Did the objects just run into each other, or was this a continuing collision? Did these objects collide 4 frames ago, and I'm just letting you know that they're still colliding and they haven't separated yet? There might be additional information you want that is message specific. For instance, if you have damage messages, you probably want to say how much damage was done, the amount of damage that was done. This kind of stuff is a little bit harder to do with methods. You can certainly have a method that has a ton of parameters, but that gets really unwieldy with some of these messages where you might have 20 different pieces of data you want to send along, and you really don't want a method that has 20 parameters in it. It's a lot easier to create an object that encapsulates all this data, and you just send the one object across. Another interesting use of messages is that you can record them for later. This is really useful in replay systems. You might have the idea of every message that is sent, we're going to write this out to disk, or certain types of messages. So if you have something like a demo mode in your game, you might play through the game, and then it records all of the messages about the input that's been recorded by the user. You write these out to disk. You can then, in replay mode, you just load this list of messages back and send them back into the system just like they originally came through. And the game is basically playing through just like you had played through it before. And you've got working demo mode with very, very little work. There's additional uses for logging. With a method, they just kind of happen. C++ is doing all of its work for you. With a message object and a message system managing things, you can record the messages. You can have another object whose job it is to deliver messages. And then you can print out stats in your debug console. You can say, here's the messages that are getting sent. You can debug draw these. You can keep stats. You can do extra profiling work. There's a lot of extra information you can get out of a message that you're not going to get with a method call. So logging. Another advantage of messages is that we can get away from the direct dispatch that method calls leave you bound to. We can have messages routed to automatically routed to multiple receivers. So one example here would be just the basic broadcast use, but we might want to let everyone in a certain area know that gravity's been turned off because the player just hit a switch. So we could do all this extra work where every time you change gravity, you loop through all the objects, find the method that says gravity's been disabled, or we just have a messaging system, and your messaging system says, hey, let all the objects know that this has changed, and then it can automatically send that message out. And it works for any message. You don't have to write a different version for each possible method that you're going to call, which is just a pain. There's also the bubbling and then the observer patterns that we'll get into. So there's a lot of other things you can do. So collision, another physics example. It's a great example where you should be using messages a lot. Object destroyed messages. This is really important for game logic. You maybe want to keep score. Whenever an enemy is destroyed, you can now bump your score up instead of having the enemies kind of do all that stuff internally. You can also have a nice generic example is the player use button. So whenever you have your player in the scene and he's walking along and you hit, say, the space bar, you send, hey, any object in front of me, I'm going to use the activate message. So what does that do? Who knows? It's up to the object to decide how it handles that. But it's a really flexible way of making the standard games you see these days where you've got a single use key and you use that one way of interacting with all the different objects in the scene. It lets you decouple things, use component-based architecture, and otherwise do all those great things we like to do. So broadcasting is pretty simple to implement. This is one of the reasons I actually recommend it as a first draft for messaging, especially if you're doing, say, game 150 or a sophomore game. There's a strong case to be made for using broadcasting. It's really simple. You have your base engine class, and then it has a list of all of your main modules in it, like the graphics engine and physics engine. And there's also then going to be your game object factory, which then has a list of all the game objects that exist. And each game object has a list of all the components on it. So whenever you want to send a message, you say, hey, engine, send this message. And it just recursively goes through all the systems and says, here's a message. The logic system, or the game object factory system says, or recursively goes through all of its game objects and says, hey, here's a message. And then the game objects go through the components, pass it on. Again, super easy to implement. It requires very, very little code, and it will work in a lot of cases. The one problem is that it can be slow. I mean, if you think about it, if you have 1,000 objects and you're sending 100 messages per frame, you're doing a lot of work every single frame. Most simpler games, however, don't have a lot of objects. They don't have a lot of messages. If you're working on a lot of like standard sophomore games, you'll maybe have a couple dozen objects in the scene at any given time. So there's really not going to be a huge performance problem with using broadcasting in these scenarios. And since there's a lot of other things you guys need to be spending your time on, if this is your first time doing a large game engine, it's not a bad idea to take the simple route and get things up and running. So just some quick implementation notes here. There's nothing really special to that. Yeah, that's pretty much whatever. So the second option then is direct delivery. This is actually also super easy to implement because it is literally calling a method. You create your message class, like collision message. You put your data in there, and then every one of your game objects and your components has a method called handle message, for instance. You take your object, you pass it to that method, and that's pretty much all there is to it. The method internally can do a switch statement or do whatever logic it needs to figure out how to handle these different messages. The limitation being is that you can't really get a whole lot of information across easily because you're literally calling a direct method. It can be combined with broadcast over very easily. You might even use like smaller versions of it. For instance, you might want to say, hey game object, here's a message, and then it's going to broadcast that to all of its components, rather than having to broadcast it to the entire game all at once. Yeah, so I mean the code is really simple for how to handle this stuff, and you don't even need to use a message object in these cases. If you want to just use the direct function call, if that's easier for you, that works. There's no reason not to use the simplest option if that's going to do what you need it to. Yeah. So observers are the big topic for this lecture. Most of what the implementation I'm going to go into is about this. The idea of an observer is that you as an object can tell and can say, I am interested in what happens to that object over there. So whenever that or a particular message of that object might raise. An example might be you are interested in the input system whenever a key is pressed. So your player object, for instance, might say, hey, input system, whenever the user presses a key, let me know, because I probably need to interpret it to move the player around or fight or do whatever it is. So the input system at this point is just saying, hey, I've got a new message available. And it goes through its list of everyone who has said, I'm interested in this message. And then it delivers it to those objects and only those objects. So it allows all the systems to be completely decoupled while still allowing a lot more efficiency than the broadcast method. The problem is that it takes a considerable amount of implementation, particularly in C++, to get all this working in a really nice fashion. But there's a few different tricks which we'll go over. So it is also extremely fast and efficient because, again, you're sending messages only to the people who are interested. You're not wasting time a whole lot. It is difficult to implement super efficiently. There's a lot of data structure kind of stuff. The implementation I will go over is not the most efficient or the most ideal, but it does work. I will leave it up to you guys to figure out how to make it a little bit better, or you can just come talk to me and we can kind of walk through it a little bit more one-on-one. Fitting some of the code for this in slides is not really feasible. So generally observers have a couple different interfaces. You have the objects that are observing things and then the objects that can be observed. Again, we'll go into that in a bit. And one thing to keep in mind is that observers tie two objects together. When object A says, I'm interested in what happens to object B, there's now this lifetime management issue. If object A is deleted, but object B is still trying to send messages to object A, you're going to crash. You're dereferencing pointers. So your observer system needs to somehow automatically deal with the situations when one of the objects is destroyed or deleted to unhook that registration for the observer pattern. Yeah, so most of the overhead is just iterating over the objects. There's CPU cache stuff to worry about. If you are working a sophomore game, you probably don't need to worry about that too much. But those of you in game 300, 400, or master's programs might care a little bit about your implementation there. And again, that's something that's kind of outside the scope of these slides. But you can come talk to me or Treb. I could certainly help you out a lot in that case. There's also the publisher-subscriber model. I'm going to bring that up only so that you know what it is, because if you search for messaging, you will see this term come up all over the place. Publisher-subscriber is kind of a more generalized version of observers. It is not super applicable inside of games. I'm aware of a few games that have used it, but it's not really like a key design pattern. It comes up a lot for internet servers. If you're writing one of these like 1,000-node internet clusters that are doing all this communication, you're writing the back end for Twitter or Facebook, you're going to be using this a lot. If you're writing a game engine, not so much. But a lot of people also confuse this with observers because it sounds really similar. The key difference is that with publisher subscriber, the subscriber, instead of registering to listen to a particular object, listens for a particular type of message. So you might say, I'm interested in key press messages. I don't care who's sending the key press message. You can kind of see the problem here is in a game engine, there's usually only one person sending key messages. And then when you're talking about general game objects, you don't care about all collision messages. You really care about that guy colliding with something. So this model doesn't really buy you a whole lot and actually has worse performance than the observer pattern. So yeah, that's just something to be aware of. Keep in mind that most larger complex engines are actually going to support a mixture of these types. It's not uncommon at all to see all of broadcast, direct delivery, and observers inside of a single game engine. Each of these have different use cases, and sometimes you need one, sometimes you need the other. Again, for most student games, you can get away with just one, or in some cases, two, broadcasting and direct delivery being the two easy options. All right, so a little bit about the message object itself. What is this message that we are sending across? The base idea is that it's a class that has a minimal amount of metadata to let somebody know what happened. One example is message type. Was a key pressed? Was the mouse moved? Did objects collide? Did an object just get destroyed? You also will often want to know the message sender. In this case, it might be, for example, in collision, it might be one of the objects that collided with something. Or if it's an object that was destroyed, it's the object that was destroyed. Because he's the one that's going to say, hey, I just got destroyed. He's sending the message out. And then there's also going to be the message payload, which is going to vary based on the type of message you're using. So here's an example, bit of an enum you can use. I've seen more complex systems that use all kinds of fancy data structures. An enum works just fine. It gets the point across. The payload can get a little bit trickier here. In this case now, you might have very different types of data for different messages. If you have an on damage message, you want to send the amount of damage and then maybe another enum that says whether it's fire damage or electricity damage, because maybe you have different resistances or something like that. For a collision message, you're going to want to know the object that was collided with. You're going to want to know where did they collide, what normal they collided at. So there's totally different types of information here. So there's a couple different ways to do this. One way that I have seen a lot of people use is just use kind of a dynamic approach. This is really popular, especially with people using dynamic languages like JavaScript or Lua. And the idea here is that you can just create a message that has a map of name to value pairs. So you maybe just put integers in there or something along that line. So when you get a message, you can say, hey, message, give me the string name normal. There's problems with that. It's not very C++-y. It's kind of slow. It's error prone. If you send a string with a different message, like you send normal with it spelled wrong inside one of your strings, then the class receiving it is going to be looking for the wrong type. There's not going to be a compile error, and you're just going to get a lot of problems. I don't actually recommend going this route unless you're actually writing your game in JavaScript or something along those lines. So a message subclass actually works a lot better. And I know there's a lot of talk about don't use inheritance a whole lot when people are first introduced to component-based design. This is actually a really good use of inheritance. This is one of the cases you really want to think about using inheritance because it works out quite well. So we've got the message-based class that has a type, for instance. So we might also have the sender. The base class is going to have all that common information that every message is going to have. We can then specialize for key message. We want to know which key was pressed. We might also want to know was the key pressed or released, a couple other bits of information. But you kind of get the idea there. And then with the mouse message, maybe you want to know where the mouse just got moved to. What's its new XY coordinate? And the collision message, damage message all has their own special information there. One thing to keep in mind is that you should prefer heavy objects. So what I mean there is we have a key message. You should not create a key up message and a key down message and a key repeat message and a shift key message. One class that has as much data as possible. It's the same thing for the mouse message. In a lot of cases, if the mouse is moving, you also want to know the relative offset. If it's moved, not only where is it, but where was it? Put that information in there. You might want to know, is the user holding down a modifier key like Control or Alt? Because you might have special use for that in, say, an in-game editor. Put that right in your mouse message. Don't require the user to wait for a key message to see that they hit Alt and then move the mouse and then let go of the Alt key. Put as much information in your message objects as you possibly can, because it's just going to make things easier. And there's really very little overhead to doing this. Yeah, you can even just use a single object for all input-related messages. And then the difference there would again be the message type might differ. So we're sending a key message every time, but the message type enum might be key up versus key down. So you can differentiate what exactly this message is about. Oh, what was that? All right, payload. OK. So message dispatch. So the idea here is how do you get the message into another object? So this is a really simple case is for direct dispatch in particular. You might just add a virtual method called handle message to your base class, for example, your base component class or a base messaging class. It takes a message, you get your base message type, and then you can do a switch on the type. For example, was it a key down? Was it a key up? In this case, you might notice that in C++, when you make your method, you are going to get a specific type. You're going to get a message as your input. So you've got to do this funky casting. If you've got a key message, you now need to cast it to the other type of, to the specific key message type. This is kind of ugly. You can wrap these up with macros. Subsonic, my sophomore game, used this with a couple macros and worked just fine. I know that it can seem a little dirty. And it also feels a little ugly to have this one method handling all of your different messages. One thing you can certainly do is just kind of make a bunch of other methods. For example, on key message, on mouse message, and inside of your switch statement, do the cast, and then just call that other method. And kind of break up this one big method into a bunch of individual messages, or methods. Yeah, so there's stuff going on there. Now another option is just make different versions of handle message for each message type. So for example, you might have handle message with type key message and handle message with type mouse message. Your problem now is you got to figure out which method you're going to call. And there are certain cases where you're not going to know that automatically. If I just give you a message pointer, it could be any of the base classes. You don't know which one it is. So figuring out which method you want to call based on that second type requires something called double dispatch. So there's double dispatch or single dispatch. A virtual function in C++ is single dispatch. I believe we go over that in CS225 if you haven't taken that yet. You'll definitely know that. Double dispatch is the case where we not only care about what is the type of the object the virtual method is on, but we also want to dynamically pick a method based on the type of the second object. C++ does not natively support this, unfortunately. So there's actually a little trick you can use to kind of implement this. You can create a new interface called message handler, and you create a new version of handle message for each of the possible message types in your game. So you got the base message, key message, mouse message, add all the other ones you want. Any object now that can receive a message will derive from this class. So now, this other little trick, where in message we have a virtual function called dispatch that's overridden. So what happens is key message is going to say, for this pointer to the base message handler, call handle message this. So what example looks like calling it. So what happens, got to explain this in code a little bit easier. When it calls handle message dot handle or handler dot handle message this, the type of this inside of class key message is key message. So when it goes to resolve this overload, it's going to decide to automatically pick the type key message. So looking at, this doesn't really illustrate it that well, but if you have a game object which derives from message handler, and then you had an object, a pointer to a message that you didn't know what the actual type of that message was, you're just going to call dispatch, which goes into message virtual function, gets routed here, and it's going to call into the exact overridden or overloaded version of handle message that exists for that type of message. So you get the double dispatch. This is a really handy technique, not only for messaging. There's actually a bunch of other places this comes in handy. It's certainly something you want to add to your toolbox for C++ programming. And again, you don't actually have to do the virtual method in the case of the message type. You can actually get away from that if you're not going to be using the base message pointers, but it really doesn't hurt to have it. So bubbling was something else I brought up. So the idea here is the way you want to take a message and pass it to all of the children or all of the parents. There's a lot of different ways you can code that. You could extend the handle message in every class. So let's say you've got your game objects version of handle message. Inside the code for that, you could say, when I receive a message for all of my components, send that message to my components. That's kind of a pain. So now every single object that has children or has a parent, you've got to duplicate this code. And it gets really error prone. It gets to be kind of a pain. But you can kind of get an idea of what we're doing here. So for example, we just hard code a run to handle message, send it to all of my children. Same thing if you want to bubble up, which is when I give you a message, you also want to let your parent object know. You just pass it on. So there's the generic method that works. It's actually a lot more flexible. It's going to make it so you don't have to keep duplicating code over and over and over again. So instead of putting that condition inside of that check inside of the handle message itself, we're going to put it inside of a base class. Or we're going to put the logic inside the base class. So here, our message handler, which can handle messages, also has a couple extra functions just to help out. We can get our parent or automatically forward messages to all of our children. These might be empty, for example, if your object doesn't have a parent, it's the root node. You can just return null for that case. And if you don't have children, then your send to children should just be an empty function. But in this case, I should have said. So here, we now have a new method inside of message called send, which is an expansion of dispatch. So when we say, hey, message, I want to send you to somebody, first it sends it directly to the handler using the double dispatch technique we went over. Then it's going to say, if this message is meant to bubble upwards, this is a message that should be sent to parents, then if the object has a parent, send it to the parent. Otherwise, if it's a message that's meant to be broadcast to all the children, then we're going to say, send to children, which again might be empty if you don't have children. All right. So again, bubbling is used a lot in UI. It's not used a whole lot in the rest of game code very often. Observers, on the other hand, are kind of the meat of this presentation. So there's a lot of different ways to implement the observer pattern in C++. I'm actually going to present two ways to do it. And again, not necessarily the best way. So the base idea of the observer is that we need to have some interfaces in C++ that understand this relationship between the objects. It understands this is an object that can observe and that this is an object that can be observed. One way to do that is with the interfaces. The other way is actually do it like C# does it. If you've used C# has a built-in concept of what's called an event. It's actually a way of handling messaging. It's built right in. It's pretty nice. You can kind of simulate it in C++, but it takes a lot of work, and it actually just uses up a lot more space. It doesn't really buy you a whole lot compared to doing it the other way, so I'm not going to go over that one. It's a lot simpler, and it's actually just, it's more memory efficient, and it doesn't really have any other downsides in C++. So I've had some working code samples for all this, so if you're kind of a little bit hazy on what's going on here, or you want to see a sample of all this working, especially some of the more heavier C++ stuff I'm going to get into a bit later here, you can get online. The code should already be up. This code is not meant to be dropped into your project. I have not given it a permissive copyright. You are not allowed to use it, and even if you were, you would not want to. This is purely illustrative code. But it should hopefully help you see kind of what's going on and get an idea of how things work. So one thing that I did is I created what's called a messaging base class. And this goes into the unbinding I talked about. The messaging base is a class that knows that when I am destroyed, I need to unhook all of the observer registrations that have happened to avoid that crashing problem. So that handles both of those cases. It includes a list of bindings. And again, the implementation I have is not ideal. It is simple and easy to understand. More of that. So quick idea, just in case it's not clear already. We've got a list of all possible bindings, and then when the object is destroyed, then we go through the bindings and say, hey, other objects that I was bound to, I'm going away, please unbind me. So the simplest way to actually implement an observer is to actually just go ahead and keep using the iMessage handler like we were using before and handle message. The only difference now is that your messages will have an additional piece of metadata. Who is the object intended for? Before, we were just kind of sending a message directly to somebody. Now we're going to say, I was sending it to object player, for instance, and we have the pointer to that object. So if you're observing messages, you might get messages that weren't originally intended for you. They were intended for someone else. And you can test this by seeing if the observer, or seeing if the recipient was not you. And then you can do whatever logic necessary that way. So another kind of quick example here, we can make a little struct. It just says, what type of message am I interested in? Is it a collision message, key message? Who is the observer? Who is the one that is being observed? And then it's really simple to just kind of set up this entry, this record, and add it to the standard vectors I had in the messaging base. Again, not ideal, very simple, it gets the job done. Now, there is a problem. So we've got, this slide is out of order. We've got a problem where we have the single handle message, but they all have to have this, there's no way to differentiate between the different types of messages you're dealing with. You've got, the observer has a handle message. We can't differentiate based on the type. Like we had the versions that were key message or mouse message on this double dispatch that was going on. It's not particularly flexible. And also, if we want to differentiate between when we're observing a message and when we're not observing a message, we'd really like to kind of have these different methods. However, C++ lacks an easy way to doing things nicely. The nice way would be what is sometimes referred to as a delegate. C# actually literally calls them delegates. A delegate is essentially a function pointer, but it also has an object bound to it. So you don't just say, like, I have this function, I want to call it. You say, I have this function on this object. And when I call this delegate, it's going to specifically invoke that method on that specific object. So it'd be nice if C++ had that built in, but it doesn't. One of the reasons for that is just the way that method pointers work. They don't work the way a lot of people would like them to work. The size of a method pointer is not like a function pointer or a regular pointer. It can actually vary based on size. There's a lot of technical reasons for, or it can vary based on your class. So in some compilers, size of a method pointer, instead of being the size of every other pointer, which is 4 on a 32-bit platform, can be up to 20. And it's not just a single compiler, but in Visual Studio, based on which type of class you're using a pointer to, or a method pointer to, it might be 4, 8, 12, or 16. There's no way to know what type it is ahead of time. There's a lot of tricks on how to deal with this. I should get into a little bit here. The ideal solution was that we would actually just have pointers to methods that worked almost like a regular function pointer. We would have a single pointer to the object and then a pointer to the method we want to call. 2 pointers, nice and easy, nice and quick. Oh, sorry. Yeah, that is the ideal solution. It is almost impossible to achieve in standard C++. I say almost because thankfully C++ lets us use little bits of undefined behavior or the little tricks that aren't really supposed to be used that we can use. Couple existing solutions. These are things you guys should all definitely look up. There's a lot of use cases for delegates besides just messaging. One of the standard ones built into C++ 11 or available as Boost before C++ 11 is the standard function or boost function template classes. One of the problems with these is that they tend to have a lot of overhead. They are completely purely standard C++ code. Because they can deal with those situations where the pointer size might be 20 or 4, and because you can also bind in C++ functors and lambdas and all kinds of other stuff, they basically work by allocating an object every time you assign something in there, and there's a lot of overhead, and it's not really an ideal use for games.
Standard function calls is stupid, very, very stupid. You can pass a float to it, and it won't even crash until you try to call it.
Yeah, so that's not good. Yeah, we definitely like compile time errors up front to warn us when we've made a mistake. Yeah, so I mean, it's not an ideal solution, but if you're in a hurry and you want something that works, it's there, it works. The more popular one, the one that I actually use a lot, or a modified version of it, is called impossibly fast C++ delegates. It's impossibly fast because in certain scenarios, it compiles down to like the ideal assembler code for making these calls. And it's more or less standard C++ as well. The biggest problem with it is that it does have kind of an ugly syntax. Just the way it uses a lot of templates, and the way templates in C++ work with functions, you got to kind of specify all of these different parameters over and over again. The compiler can't figure it out on its own, even when you really think it should, which is kind of unfortunate. But you can kind of fix that with macros. And then there's the fast C++ delegate, which is slightly newer. It is actually, it very much uses some non-standard, non-portable, portable, but technically undefined behavior, but it's actually really flexible. It has all the features of standard function, but you only pay the overhead when you use those features, and otherwise it's basically the same as impossibly fast C++ delegates. The problem is that it's a very non-trivial implementation. It is not something you probably want to spend a lot of time debugging unless you just really like using templates and abusing the compiler. Which I find fun, so I had fun playing around with that, but you guys, maybe not so much. So the impossibly fast C++ delegates is, like I said, kind of bad. This is how you bind a delegate. So you define a delegate, you specify the signature of the function, and you got to use this big old template thing, and you got to specify the class and the function. Like you see, my class is in here twice. That's kind of annoying. And then you're passing a pointer to my class, and why couldn't the compiler just figure that out on its own? It's just the way the syntax works. Again, with some macros and a little bit more template work with a macro, you can actually hide most of that. But then it's a little error prone. If someone types in the wrong thing, they get like these crazy template errors, and it's not very easy to figure out what's going on unless you're really intimate with how this works. So it's kind of a downside. And there's actually another problem. You notice that when you define the delegate, you have to define the signature explicitly. This delegate called callback fn can only take functions that return nothing and take an int and a float. But we wanted a version of our handle message that could take any message subclass. This is not going, or to do the double dispatching particularly, this isn't going to work. So we actually need to have a modified version that will let you abuse C++ a little bit more in order to get the behavior we're looking for. So thankfully, we can just take some of the core code and how impossibly fast explosive delegates worked and get where we're going. So I'm going to go a little bit here in the template magic behind how these delegates work, how it is that it's binding these method pointers into a single void pointer. So the idea here is that we have what's called a stub function called bind method. And you notice that as templates, it not only takes two types, but it actually takes a template parameter that is a method. This is called a non-type template parameter. It used to be kind of really hard to find compilers that supported it. All the compilers you should be using now should have no problem with this, though. So the idea here is that we can, at compile time, make different versions of this function for different methods. And so, I mean, obviously, if this is making you a little nervous, that's not a bad thing at all. This is kind of scary code that should not be used in most circumstances. But the idea here is that with templates, whenever you give a type to a template, it generates a new version of that function specialized for that particular type. We're doing that for methods. So if you have an on-key message and an on-mouse message, and you bind both of these to bind method, it's going to create two versions of bind method specifically for those functions. So the difference of whether it's going, the version of a method pointer that takes 4 bytes or a version that takes 8 bytes, it doesn't matter. It's actually wrapping that all up at compile time. It doesn't need to store extra information inside of the pointer. So we can now just return this function, which is actually just a regular C-style global function. It's not a method itself. It just returns void, takes a couple parameters, nothing special about it at all. You can actually convert this into a void pointer just fine. So now at this point, using that trick, we have that converted void pointer from our message or from our method, and then we have the void pointer to our base object. That was our ideal case, if you remember from a few slides ago. 2 pointers, absolute minimum amount of data, and it's actually fairly fast. It actually turns out that it's, in many cases, it's going to turn down to a fairly minimal set of assembly instructions, not a whole lot of overhead compared to some of the other methods like standard function. So an example of how you kind of set up your inner code here is we've got the observer class, has an observed key message that takes a key message. Our binding manager is internally going to have this list of the observer and the callback, our 2 void pointers. And then we can just set up the observer as the pointer to the object, and then we just take the address of bind method with, again, all this duplicated specialization, the my observer, you see there's in twice, all that kind of stuff. But you can, again, wrap this up in a macro a few cases. 2 pointers, our registration is working. Not a lot of overhead. It's nice. So that was kind of a quick overview of how to do the observer pattern code-wise. A lot of that's going to be explained a bit more if you look at the code online. Unfortunately, fitting that all into slides was just not possible. I started trying to split them up. I mean, it's enough code that it wasn't going to fit in here. I will give you some tips to kind of take this to the next step, since this is obviously a really basic system. One thing you can do is clean up the observers. There's a lot of things I did, like the standard vector for keeping the list of observers. Or the list of bindings. That's really not ideal. There's better ways to do that. Usually, you almost always want to be using standard vector for almost everything in a game. This is one of those rare cases where that's not not really true. Another thing you can do, and this is a thing I know a lot of people talk about a lot, is using metadata in games. We're going to be doing some more in-depth talks on those later this semester. So the idea here is that you can, for an object, like say you're a physics component of a game object, you can say, here are the list of messages it will send, like I collided with something, or I've stopped colliding with something. You can also then make a list of all methods on an object that can receive messages, basically any method that takes a message as a parameter. Using these lists of data, you can now make a nice GUI where the designer can just drag and drop objects and connect them together. So you can just kind of click over on one object and say, on its on collision destroy method, you take that, you drag it over onto another object's on collision message point, and then it automatically creates this binding, and things just start happening. You don't have to go into code and write all this manually. It can save a lot of time, non-trivial amount of implementation to get this working, however. Another thing you can do is observable dispatch. The idea here is that whenever I send a message to an object using the direct dispatch method, I can hook up an observer to that. So instead of explicitly saying, I want to send out a message only to observers, you can say, hey, I'm the collision system, I'm colliding with you, and by the way, if anyone else is listening, you can get the message as well. So it gives you the flexibility and the efficiency of both means, which is kind of why I said earlier that a lot of games will actually implement more than one type of messaging inside of them. And then the biggest recommendation I have is keep it simple, especially the observers thing can be a little complex, especially if you don't have a lot of familiarity with templates yet. The broadcast, the direct dispatch are totally suitable for most games, especially at the student level and the hobby level. Concentrate on getting things done that your team actually needs rather than this super fancy templated observer pattern that if your game doesn't need it, it's just a waste of time. It's a fun exercise and not actually helping you make a better game in a lot of these cases. So that is the presentation. And do we have any questions about any of that? Yes? Can you speak up? Publisher, subscriber? I'm sorry, can you speak up a little bit more?
So is the listener pattern more similar to the observer pattern or the subscriber prescription?
Which one is?
Subscription pattern.
Okay, so it's, the question is like, what are the relationships between observer and publisher subscriber? Is that right? The question is, what is the relationship between observer and?
No. So I've heard a different name for the whole registering. So the event listening system.
Yeah. There's, like I said, there's a lot of names.
So is that leaning more towards the observer or the subscription?
So it's all just terminology. People use a lot of different synonyms for the exact same thing. Some people call it binding, registration. These all just kind of mean the same thing. It's not like a hard and fast terminology. I use messaging and binding personally for observer patterns. If I were writing a publisher subscriber, I would actually call it the exact same thing. I would call them messages, and I would say you would bind. It's just instead of binding to an observer, you're now binding to a specific type of message. Otherwise, the terminology is just a way to confuse people. Any other questions? All right, thanks.